Integrated rate laws. A rate is a function of the initial concentration and the measured concentration, that is the concentration after a certain amount of time t. We get the integrated rate laws by taking the integral of the previous 0, first, and second order. So we are going to have three types that we're going to discuss in class. That is the 0 order, first order, and second order. For this section, you need to just memorize the equation. We are not going to do integrals. 0th order is independent of concentration. When we wrote the rate equation in the previous unit, we learned that rate is equal to K. The reason rate is equal to K is if we have any concentration to the power of 0, that is equal to 1. So the rate just becomes K. So if I plot rate in molars per second versus the concentration A in molars, you'll get a horizontal line. No matter the concentration of A, the rate will not change because the power is 0. If we integrate that, we will get this following formula, which says that A concentration at some time t is equal to A concentration naught, which is the initial concentration, minus KT. If I plot the A concentration in molars versus time, you will get a linear line. It is a negative slope because we have a negative in front of the K. This equation is written in the line format, in which this AT is equal to the Y, this is A naught is equal to B, and this is mx. So K is my slope, T is my x because that's my horizontal, my B is my initial concentration I started with, and AT is the concentration that is changing. Since there's a negative in front of my K, which is the slope, the K is a negative slope here, minus K. First order is dependent on concentration. Rate we defined as equal to K times the concentration of A. If I look at this equation, if the rate doubles, the concentration doubles. If the concentration decreases by a third, the rate decreases by a third. That tells you rate and concentration are directly proportional because the K here is a constant known as the rate constant. So if I plot rate in molars per second versus concentration in molars, I should get a linear line. If I take the integral of the rate equation, I will get the integrated rate law, which is written as ln concentration of A at some time t is equal to ln concentration of A naught minus kt. Remember that ln is natural log and not log. You will also see the equation written in this format. However, if you're struggling with math, this is the format you want to use. When logs and natural logs are divided, they're actually subtracted when we write them out. When natural logs and logs are multiplied, they are added. Therefore, if you don't know those properties, it's best that you use this expanded form. So when I plot the concentration of A in molars versus time in some unit, you will get an exponential curve decay. Why? Whatever amount we have, we can't have more of it. As time goes by, it's going to decrease exponentially. Second order is also a function of its concentration. However, the power or the exponent is to the second. This is why it's called the second order. So if I double my concentration, my rate increases 4 times. Why? You have to square whatever the concentration you have. And again, K here is a constant, so you could ignore. So when I plot rate, which is in molars per second versus concentration in molar, you will get an exponential curve. If I take the rate law and I integrate it, my integrated rate law looks like the following. 1 over A concentration at some time t is equal to 1 over the initial concentration plus kT. And again, this is written in the line equation format, which I'll discuss in a little bit. So if I plot the concentration A, which is in molar, versus time in unit, I will again get an exponential curve, but it will be a little steeper than the first order. I will again get an exponential decay. So the decomposition of SO2-Cl2 is a first order and has a rate constant of this. So this is my K. If the initial concentration is 1.00 molar, how long? So we're looking for time for the concentration to decrease to this. This is a concentration at some time t. My 1 is my initial concentration. If you are having difficulty with these story problems, identify the variables first. They will help. So we know this is a first order. The first order equation is ln A at some time t. This is equal to ln the initial concentration minus kT. We're solving for a t. We know every other variable. So we're going to plug in. So this is ln 0.78 molars equals to ln 1 minus k is given as 1.42 times 10 to the negative 4 to the negative seconds times t. So ln 0.78, you're going to punch that in and you get something like negative 0.248. This is equal to ln 1. If you punch that into the calculator, that's 0 minus 1.42 times 10 to the negative 4 times t. So I need to divide both sides by negative. So when I do that, my negatives cancel out. T equals to 1749.7. Now we're going to do sig figs. Right here has 3 sig figs, decimal significant digit. So that one has 3. 0.78 has 2. And my constant here has 3. So least amount, so I need 2 in my answer. 1, 2, I look 1 to the right. So it stays. I need zeros for a placeholder. And here the seconds cancel out. There's a seconds in the denominator. It comes up. So my units are seconds. B, if the initial concentration of SO2-Cl2 is 0.150, that's my initial. What is the concentration of SO2-Cl2 after 500 seconds? So this is my time. I already know my K from above. So we are looking for AT. Equation is the same because it still has to be a first order minus KT. So I'm going to plug my numbers in. So if I plug my numbers in, I have ln. This is ln 0.150 molar minus my K is 1.42 times 10 to the negative 4 seconds to the first. This is 5.00 times 10 to the 2 seconds. The seconds cancel out. So I'm going to simplify my math. So this is still going to be ln. And when I take the ln of 0.150, I'm going to get negative 1.897 minus, if I multiply 1.42 times 10 to the negative 4th times 5 times 10 to the second, I'm going to get 0.071. Next, I need to add everything in my right side together. Since they're both negative, they're going to come out as negative 1.968. This is going to be equal to ln A. To get rid of the natural log, we need to do the anti-natural log. Raise it to the E on both sides. So on your calculator, on your calculator, it will either be a shift, depending on your calculator, and ln, or it will be second and ln. You should get E that appears on your calculator. The concentration of A becomes 0.1397, and this will be in molars. Pause the video, try this problem on your own, and then check your answer. So this problem is also first order. The rate constant for this decomposition is given as this, so that's my K here. What is the half-life of this reaction? So the half-life for a first order is T is 1/2 is equal to ln 2 over K. Please note that T is equal to time. T 1/2 is half-life. They do not mean the same thing. And if you notice, you will be using both. Time is the time that they tell you to solve for. T 1/2 is the time it takes for concentration to decrease by 50%. So if I plug this in, this is ln 2 divided by 6.82 times 10 to the negative third seconds to the first. So T 1/2 equals to 101.63. So with sig figs, there are 3 sig figs because it's scientific notation. So this becomes 1, 2, 3. I look 1 to the right. 102 units of seconds. I know I didn't do a lecture on this in the video prior. However, we did it in class, so this is why I did the problem. Pause the video, try this problem on your own, and then check your answer. So here we have a reaction A is a second order. This is a second order with a K. So they gave you the K constant as 0.133 molars to the first, seconds to the first. If the concentration A is 0.395, so that is my initial concentration, A naught. What is the remaining concentration after 43 minutes? So this is my time. We're looking for the concentration of A at time t. So since it's second order, my equation is concentration of A at time t is equal to 1 over the initial concentration plus kT. Plugging my numbers in, this is equal to 1 over 0.395 molars plus 0.133 molars to the first, seconds to the first, times 43 minutes, which needs to be converted because this is in seconds, this is in minutes, so the units have to be the same. I'm going to convert my minutes, so diagonals have to be the same. 1 minute has 60 seconds. You could also convert the seconds down here, but for most of you, it's in the denominator, so it's going to be a little bit harder. So now let's do the math. So this equals to, if I take the reciprocal of 0.395, that is 2.5316. If I multiply this entire thing, I get something like 333.14. This is equal to 1 over it. So now I need to add these two numbers on the right side. You should get 345.67 is equal to 1 over AT. So AT equals to 0.0028929. So you could solve this math algebraically by cross-multiplying here or rearranging the algebra. So doing sig figs, I have 3 sig figs here. I have 3 sig figs here. Only 2, so my final answer has 2. I start from the left, go to the first non-zero digit, which is a 2. 1, 2, I look 1 to the right. It goes up, so this is 0.0029 molars. To make the math a little bit easier, on your calculator, if you punch in your A naught number and then x to the negative first, this is the same thing as taking the reciprocal. So for this problem, we had 1 over 0.395 molars. So the way you punch this into the calculator it would be 0.395, and you would do the reciprocal button and it will do this math for you. It is up to you which way you want to do it. Just do the algebra correctly. Pause the video, try this problem on your own, and then check your answer. So this is a zero order. The rate constant is given as 5 times 10 to the negative 4. So this is my K. The initial concentration is 0.0800. So that is my A naught. What time? So we're looking for T when it reaches 0.0300. So that is my A at time T. Since we know this is zero order, my equation is A at time T is equal to A naught minus KT. So plugging in, this is 0.0300 molar. Initial is given as 0.0800 molar minus 5.00 times 10 to the negative 4th molars per second, T. T equals to 100 seconds because all the molars cancel out and we have a seconds in the denominator. Now we need to go back and do sig figs. K, the exponent doesn't count, so everything in front counts. So there's 3 here. There's 3 for the initial. Decimal significant digit, these zeros are significant. Decimal significant digit, so those zeros are significant. Everything has 3. I have 1 in my answer. So there are 2 ways you could write this. I could put a decimal, and if I put a decimal at the end, since there's a significant digit, all these zeros are significant. Or I could write in scientific notation to the third, or I could write in scientific notation times 10 to the second, because in scientific notation, everything in the front is significant, seconds. So when I was going over 0, first, and second, I wrote all the equations to resemble the equation of the line, which is y equals mx plus b. So for zero order, the integrated rate law was the concentration of A at some time t is equal to negative kt plus the initial concentration. The concentration at time t is my y, kt is my mx, and my A, or my initial concentration, is my B. My initial concentration here is the y-intercept. My time is my horizontal axis. That makes my K the slope. Since it's negative K, my slope is negative. For first order, the integrated rate law was ln concentration of A at some time t is equal to negative kx plus ln the initial concentration. It was written in the line equation format. Ln A at some time t is your y, minus kt is your mx, and ln initial concentration is your b. So here is your y-intercept. My t is my horizontal axis, x. So negative k is my slope, and my ln A at some time t is my y. This is why my slope is negative for the 0 and the first order. For my second order, my equation was 1 over A concentration at some time t is equal to kt plus 1 over the initial concentration. Again, written in the line equation format. So 1 over AT is my y. This is equal to mx plus b. So my initial concentration is my y-intercept. My t here again is my x, or horizontal axis. My k is my slope. If you notice my k is positive, this is why the slope is positive. So 1 over A concentration of t is my y. How do we know it's a 0, first, or second order? We look for the graph that gives you a linear line. If it's a 0 order and I plot concentration of A versus t, I should get a linear line that's a negative slope. If it's a first order, if I plot ln concentration of A versus t, I should get a linear line with a negative slope. If it's a second order and I plot 1 over a versus t, I should get a positive linear slope. Every other graph will give you a curve. This is how you differentiate if it's 0, first, or second based on data point. If I look at this, I plotted the concentration of A, plotted ln concentration of A, and I also plotted 1 over concentration of A. So for 0 order, only the concentration of A versus time will give you a linear line. And if you look at this, this is a negative k, the slope. If I plot ln concentration of A or 1 over concentration of A versus time, they all give you curve. In the first order, the only one gives you a linear line is ln concentration of A. This gives you a linear line that is a negative k, so it's a negative slope. Every other graph gives you a curve. For the second order, the only thing that gives you a linear line is 1 over A. This gives you a positive slope, k. Every other curve gives you a line. This is why for 0 order, the equation is A equals to A naught plus KT minus KT, because the A here, right here, gives you a line. Everything else gives you a curve. For the first order, my equation is ln A equals to ln A naught minus KT. Why? This is the only plot that would give you a linear line to identify it's a first order. And if you notice, the slope is negative for both of these. For second order, the equation is 1 over A naught plus KT. Why? This is the only plot that gives you a linear line. The k is positive. So the equation will tell you which one will give you a linear line, identifying its order. How can you tell the difference among 0, first, second order rate laws from their graphs? 0th order, you'll get a linear line when it's concentration of A versus T. First order, linear line will occur when it's ln concentration of A versus T. If it's second order, linear line will occur when it's 1 over A versus concentration of T. Determine the order for the following reaction. You have this data table. Based on this information, you cannot tell 0, first, or second. Since a data table is provided with time and the concentration of the reactant, what you need to do is you need to plot these. So that means you need to do a table with concentration of A, concentration of ln A, and concentration of 1 over A. The information given is my information for 0 order. So what you're going to do is you're going to take this number and you're going to take the natural log of it. To get this information, you're going to do 1 over concentration of this number to get the values for this. After you do that, you need to plot versus t. If you punch the numbers into the calculator correctly, these are the values you should get. The second column was given, but it's still the initial concentration A. Using the initial concentration, you did the natural log of each of the values, and then using the initial concentration, you did the reciprocal of each of the values. Like I told you in the previous slide, you need to plot each one. If you plot concentration of A versus T, ln concentration versus T, and 1 over A versus T, you will get these plot. The only plot that is linear here is the middle plot. That tells you data represents a first order. You cannot guess on these. You actually have to plot them to figure out what they look like. Half-life, written as T1/2, is the time it takes for concentration of the sample to decrease by 50%. So for 0 order, we know the rate law and the integrated rate law. The half-life for 0 order is T1/2 is equal to the initial concentration divided by 2K, in which K is the rate constant. For first order, T1/2 is equal to the natural log 2 over the rate constant K. For second order, T1/2 is equal to 1 over K times the initial concentration. You need to memorize all the integrated rate laws and the half-life formulas, as well what they look like graph-wise. So let's look at this first example. The half-life of the first order is 13 minutes. So that means this is my T1 half. The initial concentration of the reactant is 0.085. So this is A naught. How long does it take? So that we have the time for the concentration to drop to 0.055. So that is my concentration at time t. So since we know this is a first order, we know the formula is going to be ln A at time t ln A naught minus kt. We have all the variables except for k. We could solve for k because we know this is a first order. T1 half is ln 2 over k. This is equal to 13 minutes. So k is equal to 0.0533 minutes to the first. Now I'm going to plug in. Going to be ln 0.055 molars equals to ln 0.085 molars minus my k, which is 0.0533 minutes to the first t. So t is equal to 8.167. So now going back and doing sig figs, there are 2 here. This 0 is not significant because there's no significant digit in front. T1 half, 13 is 2 sig fig, and then 0.055 is also 2 sig figs. This is just a placeholder. So my final answer needs 2. I start on the left, 1, 2. I look 1 to the right. So this becomes 8.2 units of minutes because the molars will cancel out with, because there's a minutes on the bottom, so it has to become minutes. Pause the video, try this problem on your own, and then check your answer. This is a first order reaction. The initial concentration is 0.64, so that is my A naught. My half-life is 30, so this is T1 half. Calculate the concentration of the reactant. So we are looking for AT and then 60 seconds, so this is my time. So my equation is ln. We are looking for ln AT, so that means we know all the variables. So we need to solve for K. Half-life is given first order. 1 half is equal to ln 2 over K. This is equal to 30 seconds. So K is equal to 0.0231 units of seconds to the first. Now I'm going to plug into the equation. So if I plug in, this is ln. The initial concentration is 0.64 molar minus my K, which is 0.0231 seconds to the first. The time is given as 60 seconds. A is equal to, this equals to 0.160047. We need to go back and do sig fig. So right here, there's 2 sig fig. There's a decimal significant digit, so those zeros are significant. So there's 3, and then there's 3 here because there's a decimal significant digit in front, so those zeros are significant. So least amount is 2, so 1, 2, I look 1 to the right, 0.16 molars. On B, how long will it take for the concentration of the reactant to decrease to 0.040 molar? Since it's the same reaction, the K is going to be the same. This is my AT. We're looking for time, and we started with the initial concentration of 0.64. So we're going to use the same equation, ln, and we're going to solve for time, ln initial. So my final concentration is 0.040 molar. My initial concentration is 0.64 given above, minus, we know what our K is because the K is the same for our given reaction, and T, so we're going to solve for T. 20.346. Sig figs, there are 2 here. Decimal significant digit, this 0 is significant, but this 0 is not. There's 2 here. There's 3 significant digits here. This is a placeholder, so I need 2. 1, 2, I look 1 to the right, it stays. If I leave it as 20, there's 1 sig fig, so I need to put a decimal, or you could write it in scientific notation. Units of seconds, because this is seconds. Pause the video and try this problem on your own. It's a continuation of the previous problem. So this is also still a first order because it's the same problem. So it's ln. So here initial concentration was not given, so I'm going to do 100. You could start with 1, it doesn't matter. So my initial is 100. We're looking for time here. K still has to be the same. K will change later when the temperature changes, but when the temperature is the same, K will not change. We're looking for T. So my final concentration, it decreased to 1/8 of its initial, which is 12.5 if I put molars. Why? It decreased to 1/8. So whatever number you start with, you just need to take 1/8 of it. That means 7/8 of the subs decayed or disappeared. So T equals to 90.019. Sig figs, it's going to be dependent on the K, so there's just going to be 3. 1, 2, 3, I look 1 to the right, and units of seconds. Because 1/8 is a number, and these are arbitrary numbers that I wrote. Pause the video and try this problem on your own, and then check your answer. This is the first order decay. The half-life is 12.3 years, so this is T1/2. How much of the 1.50 milligrams? So that is my initial. And this is my time. So I am looking for my final, which is AT. So my equation is ln T. This is ln naught minus KT. I do not know my K, but I know my half-life for first order is ln 2 over K, and my half-life is 12.3 years. K is equal to 0.05635 years to the first. And so now I'm going to plug my numbers in. So ln 1.50 milligrams, and we could leave it in milligrams, minus K, which is 0.05635 years to the negative first, times my time, which is 49.2 years. This is going to equal to ln of AT equals to negative 2.36695. So now I need to do the anti-natural log. So this is going to be E, and then this is going to be E. So AT equals to 0.09376. Now we need to do sig fig. There are 3 in my half-life. There's 3 in my initial concentration, decimal significant digits. So this 0 is significant, and 3 here. So my final answer has 3. I go to the first non-zero digit, which is 9. 1, 2, 3. I look 1 to the right, so the 7 becomes an 8. So it's 0.0938 units of milligrams, because this was in milligrams. So for integrated rate laws, you need to just memorize the equation given. You cannot do the integrals from the rate laws to get the integrated rate laws. The best way to memorize it is in the expression similar to the line equation. Memorize their half-life. The way the integrated rate laws are written will tell you which graph will produce a line. So for example, zero order is concentration versus time, and the equation is written as concentration. For first order, the equation is written with natural logs. So when you plot the natural logs versus time, you will get a linear line. For second order, the equation is written 1 over the concentration. So when you plot 1 over the concentration versus time, you will get a linear line. The linear line will identify the order. So when you get a data table with time and initial concentration, you need to plot concentration versus time, ln concentration versus time, 1 over concentration versus time, to determine which order the equation represents. You cannot just guess on it. Once you know what the order is, you can solve the rest of the problem. Memorize the half-life. Make sure you know how to use your calculators when you are doing natural logs and logs. Natural logs are ln, logs are log.